This is our lesson on the compound angle formulas, and we're going to start by proving one of these formulas, showing you where this formula comes from. So we have a unit circle here. Unit means its radius is 1, and the 1's kind of covered up there, but these are all 1s and negative 1s all the way around. And I've got two angles, kind of arbitrary angles drawn on there. We're going to call the first one A. So let me I'll use red so that I try to color code this. So we're measuring from the positive x-axis over to, let's call this one here. That's going to be our angle A. That's theta 1. Theta 2 will be B. That's this, and the first one here, that's in the first quadrant, that one will be B. We've got theta 1 is A and theta 2 is B. So what the angle between those two? So if I'm looking for the measure of this angle in between these two blue lines, that would be the measure of angle A subtract angle B. So that's A minus B. The lengths of each of the blue lines, I said that at the beginning, those are each 1. Okay, so where are we going next here? Next, we're going to label the points where the blue lines intersect the unit circle. We're going to start with A, that's our red one. So up here, I'm going to put a dot. This is a coordinate. And remember that X is cos and Y is sine. So instead of me just calling it an X and a Y, this is cos of angle A and sine of angle A. That's the first point. The second one is, well, so actually the first one was kind of doing this backwards, but our other one here is going to be B. So X is cos of B, and Y is sine of B. What we're doing right now is we are developing some parameters. We're developing some values or variables that we can use to come up with a formula. And now, yeah, if you've forgotten why cos is X and sine is Y, you've got that in your grade 11 notes. You can look that up. Next thing, we're going to draw a line in between these 2 points, and we're going to call it C. So try and use your ruler to draw a line between those 2 dots on the unit circle. There is a line, and we're calling that line C right there. For this new triangle, so kind of the black and blue triangle here, write out and simplify the cosine law. Let me erase this blue that's here. So the cosine law for that new triangle. The cosine law, I will put it off to the side. I think I can put it in. Cosine law. C squared, that's the black C that I just put in there. C squared is equal to, and then we do our 2 sides squared. In this case, both of our sides are 1, side lengths are 1, so it's 1 squared plus 1 squared. The next part of the formula is minus 2 times B times C. Now, in this case, 2 times A times B, our A's lengths are A is 1 and B is 1. Those are the blue lines, they're both 1. Times cos of the angle in here. This is the angle, I mean cos of that angle. And remember what we called the angle there, A minus B. So cos of A minus B. We're going to clean that up a bit. We have C squared equals, so 1 squared plus 1 squared, that's going to be a 2, minus 2 times 1 times 1, that's just 2 cos A minus B. Okay. So that's that's as far as we can go, because when you look at that cosine law formula that I used, I've got 3 variables, a C and an A and a B, and you can't solve one equation with 3 unknowns. We would need 3 equations to solve that. So right now we've got 3 unknowns. We're kind of stuck here. This is the same triangle that we just had. It's just a much more nicely drawn one. Everything else is the same. So here's a formula that we just wrote on the last slide. That's called equation 1, and we're stopping there because we don't know we don't know anything else. We don't know A, B, or C to sub into that. Well, looking at C here, my next step, and you would never think of this on your own. When you're first doing a proof, you usually have to follow someone else's proof, and I wouldn't have thought of this on my own either. But the next thing, we've got to get rid of some of these variables. So let's change C. We're going to use a distance formula to find the length of C using its endpoints. Do you remember the distance formula? It's got that big square root sign all around it. There's x2s and x1s and subtractions and squares and all kinds of stuff there. When we substitute into it, C is equal to, so this is substituting into the distance formula. So instead of x's and y's, I've got cosine, sine. Those are x's and y's, right? That's x1, y1, x2, y2. Subbing into the distance formula. So what should we do next? Well, it's pretty hard to, we've again got a C and A and B's all over the place here. So we're stuck again with three variables, but we're going to try to square both sides just to get rid of that radical. If we square both sides, then we don't have the radical anymore. And what I can do now, this is just a binomial. Imagine this were x minus y squared. We would just expand the binomial. Same thing here. We're going to use binomial expansion, and that works out. You'll have to trust me. I'm not going to spend all the time doing it. It works out all like this here. Okay, this is all the binomial expansion. So this is getting to be a bit cumbersome. Why are we doing all of this? Well, because it's in the ministry expectations. The curriculum says that you have to be able to explore the algebraic development of the compound angle formulas. But the good news is, student reproduction of the general case is not required. So you do have to understand how this works, but you don't have to reproduce it from scratch or from first principles. So there's often a quiz or a test question that asks you to do a little part of it. Like I might say, what's the next step after here? Or expand these sides or something like that. One piece of it, but you do not have to reproduce the whole thing. You don't have to know how to do it all yourself. You just have to know how to kind of apply parts to it. Okay, let's get back to work here. We've got our first equation. That one looks a lot nicer compared to where we're at here with this equation. And I'm going to introduce another piece of information, and that is our Pythagorean identity is sine squared plus cos squared equals 1. So sine squared plus cos squared equals 1. We're going to collect some like terms in here. We've got some like terms. You should be able to see them yourself. And we simplify it to this. When we collect our like terms and we use the Pythagorean identity, we get this equation. So now we have that simplified a little bit. And remember our first equation? This was the original one we came up with here using the cosine law. So what do you think we should do next? We've got C's, A's, and B's everywhere, but these are both equal to C squared. So if they're both equal to C squared, then I can make them equal to each other. So here's equation 1. I'm sorry, that one's 2. Yeah, that's 1. That's equation 1. And there's equation 2. That's this one right here. I put them together. What we're going to solve for is cos A minus B. That's what we're going to solve for or isolate. So here's a negative 2 cos A minus B. And I'm going to bring this 2 over to this side, and then I'm going to divide everything by negative 2, and we are left with this piece right here. And what this is, we can't go any further. We've got A's and B's, 2 variables, but that is the cosine formula, compound angle formula for subtraction. So this you need to memorize. It's not that hard. You've got cos A cos B plus sine A sine B. So whatever this sign is here, it's a minus. You're going to put the opposite sign in here. It's a positive. This is our first compound angle formula. We are currently able to find exact values in radians using the special triangles or the unit circles. So what we're going to do now is we're going to find an exact value. We're going to use a formula that we just determined. We're going to use that formula. We want to find the exact value of cos pi over 12 without a calculator. So this is you're preparing yourself for a non-calculator quiz or non-calculator test here. And some of our calculators won't give us an exact answer anyway. Some of you, they will. Some of you, when you put this into your calculator, will give you the exact answer. But that's why you have to show me you can do it without the calculator. So we want the exact value of this number, right, of cos pi over 2. Sorry, pi over 12. We've got two. I'm going to show you two different methods. Two methods. The first method here, I'll put a 1 here. First method that we're going to use, we're going to work in radians. Radians. Okay. We've got, I'm just going to look at that angle. The angle is pi over 12. That angle. I don't have, so this is pi over 6, pi over 3, pi over 4. This one is 0, pi over 2, pi, 3 pi over 2. I don't have any pi over 12s here anywhere. There's no pi over 12 values here. So I don't have a triangle I can look at and find cos of pi over 12 by doing the opposite over, by doing the adjacent over the hypotenuse of some triangle. I don't have any pi over 12 relationships. But this is why we're learning what we're learning here. I can write pi over 12 as two different fractions. So forget about the pi for a minute. Imagine you have 1/12. Imagine you just had 1/12. How can I write 1/12 using these denominators that I circled up in red? So another way to think of it as, let's start with 12s first. I want to use my new subtraction formula. So two numbers that I would subtract to get a 1 for the numerator. Okay, that's easy. I could do 10 minus 9. That's 1/12. I could do 7/12 minus 6/12. That's 1/12. I could do 2/12 minus 1/12. These all work. I could also do, there's lots, and hopefully you're coming up with some on your own course. There's all different ways. I'm trying to get a 1, so I want to subtract. I could do 9/12 minus 8/12. Any of those are going to give me 1/12. So the pi, that is really the question, we really have a pi in our numerator. We're kind of ignoring that for now. We're just thinking that as 1 pi or a 1. All of these are ways I could get pi over 12 or 1 over 12. I still don't have any triangles with denominators of 12. But many of these numbers reduce. For example, 2/12, the bottom one here, that's the same as 1/6 minus 1/12. Now I do have a 6 denominator. So I could use that one, but I don't have a 12th denominator. So I'm going to look at all of these ones that I came up with, and I want to find a pair that I can reduce both of them, so that I can reduce them both and they will have denominators I can work with. So I'm going to use, I'll use this top one here. You don't have to, but I'm going to use that top one there. So I'm going to rewrite pi over 12 over here on the right. I'm going to change that to 9 pi over 12 minus 8 pi over 12. So now that's the same as 1/12. 9 pi over 12 minus 8 pi over 12 is 1 pi over 12. But the reason I picked those is because they reduce. 9/12 is the same as 3/4, and 8/12 is the same as 2/3. And there are other ways to do this. This isn't the only one, but this is just the one I'm going to do. You could also have used, you could have done 4 pi over 12 minus 3 pi over 12. Those both reduce as well, so you could have used that one too. But we'll stick with this first one here. Okay, so we've got, oops. Actually, I will put them both down because I said I was going to do this two ways. So I'm also going to write pi over 2 can also be written as, use a different color. We could also write it as 4 pi over 12 minus 3 pi over 12. So that's also 1 pi over 12. And reducing those gives us pi over 3 minus pi over 4. Now, those ones are actually a little easier because the numbers are smaller. So we are going to do them both. Let's start with that one. So I'm just going to press pause here and I'm going to erase all this fraction stuff I have to give me some more room. All right, let's get back to the question here. The question was determine the exact value of cos of pi over 12. Well, as I determined up here, I don't have a pi over 12 triangle or angle to use. So instead of that, I'm going to find cos of pi over 12 is the same as I could use either of these two here. They're both the same. I'll use the bottom one because I think it'll be a little easier. Pi over 3 minus pi over 4. Those, what I've written there in red, those two lines are exactly the same as each other. What is not correct right now, if you're thinking, is to distribute, for example. You cannot distribute a function. So I can't distribute cos and say, well, that's cos of pi over 3 minus cos of pi over 4. It's not. We can't distribute functions like that. What we can do is we can look at the formula that we just figured out. So I'm going to use the formula. Look at the formula. The formula was if you have cos of a minus b, that's the same as cos a times cos b plus sine a times sine b. So I'm going to replace my a with pi over 3, and I'm going to replace this b with pi over 4. So I'm just going to substitute in to this formula, in for the a's and in for the b's, my pi over 3 and my pi over 4. So I'd like you to press pause right now and do it yourself just to make sure you have this step right. So go ahead, press pause, write it out, and when you come back I will have the whole answer written out for you. So here we go. I took this piece right here, which is the same as my left side, except instead of an a and a b, I have a pi over 3 and a pi over 4. And then everywhere I had an a, I replaced it with a pi over 3. Everywhere I had a b, I replaced it with a pi over 4. And this is my new little equation here. So we don't just distribute the cosine, that's wrong. We have to use our formula, and we've proved the formula already. So we already know where this formula comes from. So now we can go back to our knowledge of the radian angles. Cos of pi over 3. So I look for a pi over 3 angle. Here it is, pi over 3. Cos of pi over 3 is adjacent over hypotenuse. So cos of pi over 3 is 1 over 2. So instead of cos of pi over 3, underneath it, I'm going to write 1 over 2. Cos of pi over 3 is 1 over 2 times cos of pi over 4. What's cos of pi over 4? Here's my pi over 4 angle. Cos is adjacent, that's this side, over hypotenuse, that's that side. So cos of pi over 4 is 1 over root 2 plus sine of pi over 3. Sine of pi over 3, you go up to your pi over 3. Sine is opposite over hypotenuse. Sine of pi over 3 is root 3 over 2 times sine of pi over 4, 1 over root 2. That gives us, we multiply these two together and we have 1 over 2 root 2. I have a radical in the denominator, I'm going to have to deal with that. Multiply these two together, I'm going to have root 3 over 2 root 2. Well, luckily our denominators are the same. I have a common denominator. My denominator is 2 root 2. When I add the numerators, I have 1 plus root 3. But I've got to rationalize the denominator. To rationalize the denominator, I'm going to multiply by 1. And my 1 is going to look like a root 2, because I have to get rid of that radical, over a root 2. That's a 1. So distributing here, both binomial parts of the numerator get multiplied in there. And 1 times root 2 is root 2. Root 3 times root 2 is root 6 over 2 root 2 times root 2 is 2 times root 4. I'll fix that up in a second. Root 4. That is, I'm going to have to write it beside here. That is root 2 plus root 6 over 2 times 2, which will be a 4, because the square root of 4 is 2. So there's our answer. And some of you may have a calculator that when you put this right into your calculator, it jumps right to the answer for you. Okay, fine. That's fine for checking your work right now when you're doing your homework, but you're not going to get to use that calculator, so don't rely on it to do the work for you. Let me erase that. So here's another way to do the same question. We are going to, instead of doing radians, let's try it in degrees, because I know some of you still aren't comfortable with radians and you want to do all your work in degrees. No problem. Let's start with that pesky pi over 12 again. Pi over 12, what is that in degrees? How do we do that? Remember? Well, you take your pi over 12 and you multiply it by 1. And this time our 1 is going to be 180 over pi. That gives us pi over 12. These cancel out. 180 over 12 reduces to 15 degrees. Okay, pi over 12 is 15 degrees. So now, do I have a 15-degree triangle up here? Do I have a 15-degree triangle? No, I didn't have a pi over 12 triangle, so of course I'm not going to have a 15-degree triangle either. These ones, if I fill them in, this one's a 30, this one is a 60, and then these are 45s up here. So how could I use the 30, the 60, the 45? How could I subtract them to get a 15? So the same idea I had here. I wanted to subtract to get the pi over 12. I want to subtract to get 15. So there's a couple of different things you could do, right? Just change colors for a second here. 15 degrees is equal to 60 minus 45. That's 15 degrees. 15 degrees is equal to 45 minus 30, and so on. So just like we had a couple of ways to get pi over 12, we have a couple of ways to get 15, with really an infinite number of ways. So we're going to pick one of these here. Let's do the first one, 60 over 45. So instead of, my original question was cos of pi over 12, I'm going to say that that's equal to cos of, first of all, 15 degrees. And cos of 15 degrees is the same as cos of 60 minus 45 degrees. You don't need to write degrees in every line here, but you do at the end. So just remember to put them in at the end. Okay, now remember, you don't distribute. I'm not going to distribute that cos into the brackets. What I am going to do is go up to my formula up here. Everywhere I had an A, I'm going to put a 60. So all these A's are going to turn into 60s. Everywhere I had a B, I'm going to put a 45, 45, 45. So again, press pause, write out the formula using degrees this time. All right, I've got it all written out now. What's cos of 60? Okay, so I don't have my degree triangles here. I have my radian triangles, but I know that 60 is the same as pi over 3. So cos of 60, adjacent over hypotenuse, 1 over 2. So I'm going to fill that in. I'm going to get 1 over 2. And then I've got cos of 45. Cos of 45 is 1 over root 2. Then I add sine of 60. Sine of 60, we go up to our 60-degree triangle. This is 60 right here. Sine is opposite over hypotenuse, root 3 over 2. And sine of 45 is 1 over root 2. Well, look at this. It's exactly the same as this line right here. So you get the same thing. I don't need to go through the math again. We are exactly at the same spot because I picked the degrees that would match the radians that we did for the same question. So we get the same answer. That is how you use the subtraction formula for cosine. So actually, I lied. I'm not going to make you memorize that formula. I will give it to you on your test. So you'll be given this formula on your test. And all of these, we went through the cosine formula, but there's one for sine and there's one for tan as well. And we're not going to go through the development of each of the formulas because it's really the same process that we did here. Example 2. Last class, we worked with cofunction identities. Prove the following cofunction identity using a compound formula. So remember all that work we did yesterday, and I said how you can represent cos several ways or sine several ways. So this was one of them from yesterday, but we're going to prove it using this identity here. This is sine A minus B. There's our A minus B. So we're going to use this formula right here to prove that cos of theta is equal to sine of pi over 2 minus theta. So let's first write down my question. I'm looking at the sine pi over 2 minus theta, and I want to prove that that's equal to cos theta. So I look up to this formula right here, and my A is going to be a pi over 2, and my B is going to be a theta. So I'm going to change all the A's and B's here for pi over 2 and theta. So again, press pause, fill it in yourself, and then when you come back, you'll see the answer. This one's different from the last one because I have a theta instead of just having different radian measures. Sine of pi over 2. What is sine of pi over 2? Pi over 2 is at the top of the unit circle. That's pi over 2. That's the same as your 90 degrees right there. What's the coordinate right there? The coordinate is 0, 1. Remember that your x is the cos and your sine is the y value. So sine of pi over 2 is 1. And cos of theta, that's a weird one. I'm just going to leave that cos of theta. I don't have anything to evaluate there. Minus cos of pi over 2. Back up to our unit circle. Cos of pi over 2 is 0 times sine theta. Let's simplify this. What we have is cos theta minus 0. So I'm not even going to write that, minus 0. So there, we just proved it. Here's the question. Right? We wanted to prove that sine of pi over 2 minus theta is equal to cos of theta, and we just proved that. So we can use our little Latin acronym here, QED, when you've proven something, but you've just shown it here. You've shown that sine of pi over 2 minus theta is equal to cos of theta. Now, to give you some perspective on what that means, we're going to look at the graphs that go along with this kind of algebra that we just did. There's sine theta. That's just regular sine theta. Now sine negative theta, so there's a negative inside the bracket, and that means that's your k value is negative right there. Got a negative k value. So imagine this with a negative k value. That means flipping it horizontally, switching it this way. Looks like that. Now the next thing I want to do is, so there's my negative theta, and I've got a pi over 2 in front of it. I'm trying to make it match the question that we just did. So I'm going to do the pi over 2 last. So I've got to do a phase shift of pi over 2. And look at what we have here. Look at this red graph that you see here. What is it? It is cos. So with transformations, I have shown that sine pi over 2 minus theta is also equal to cos theta. This is the cos graph, and we got it from a reflection and a translation, which is a lot what we talked about in our 7.1 in our last lesson. Not only do we have subtraction formulas, we have addition formulas, so you don't have to memorize them. It's good right now, though, if you start a sheet with all these formulas on it, because you're going to get more. We've only started chapter 7. You're going to get more, and it's good to have a handy reference page for yourself, so you're not always flipping back through your notes to find these formulas. So now we can find something like 5 pi over 12 by adding two numbers instead of subtracting. Or our original question was a pi over 12, so we can now add angles. Use the appropriate compound angle formula to determine the exact value here. Then determine the exact value another way and check your first answer. Remember, this is not the same thing as just distributing the sine and finding sine of pi over 6 and sine of pi over 3. And some of you will do that. You'll forget that and you will just distribute it. You can't distribute a function into the angles. You can't. That's not like It's not like this is a 5 in front and then you could use a distributive property. It's actually a function that requires an angle. So we can't distribute the way some of you will be inclined to distribute. We've got two methods here we've got to do again. We've got to find two methods. So let's start with method 1 here. Method 1 we're looking for, let's write down the question, sine pi over 6 plus pi over 3. We're looking for sine of that. So I'm going to go right to my formula right here. A's get switched out with a pi over 6. B's get replaced with a pi over 3. Okay, press pause and do it. There we go. Hopefully yours matches mine. I've got pi over 6 and pi over 3, so I'm just going to throw my little triangle up here. Didn't draw it very well, but we'll call this the pi over 6 angle. This is the pi over 3. And yes, you could be doing all this in degrees right now. You could convert pi over 6 to degrees, and you could convert pi over 3 to degrees and do it all in degrees if you wanted to. But radians are better, so we're stuck with radians here. Here's my right angle. If I'm going to start with sine of pi over 6, here's pi over 6. Sine is opposite over adjacent. What are my side measurements? So we're going to fill in our side lengths here for pi over 6 and pi over 3. Pi over 6 is the smallest angle. That gets a 1. Pi over 3, across from the pi over 3 is the root 3. And then our hypotenuse, 3. And then our hypotenuse is 2. Sine is opposite over hypotenuse. So that's a 1/2. I'm not going to keep doing that for each one. Just did it for the first one. That's a 1/2. Cos of pi over 3 is also 1/2. Plus cos of pi over 6, root 3 over 2. And sine of pi over 3 is also root 3 over 2. Multiplying 1/2 times 1/2 is 1/4. And root 3 over root 3 is root 9 over 4. So putting that together, we have a common denominator of a 4. And that's really a 3, right? Square root of 9 is 3. So 1 plus 3 over 4 is 4 over 4, which is 1. That is one way of doing the question. But there is another way for this one. This one's kind of a unique one here. So let me show you method 2. And method 2 in this case is not me just doing the same question in degrees. Method 2 here. Method 2. Here's the question. Sine of pi over 6 plus pi over 3. So what other way could there possibly be to do this? Well, in this case, these two, when I add them together, these together, pi over 6 plus pi over 3, that's really, common denominator would be a 6. And that would make this a 2 pi over 6. That's really sine of 3 pi over 6, which is sine of pi over 2. Sine of pi over 2, pi over 2 is one of my angles that falls right on the axes, right? Pi over 2 is up here, it's 90 degrees. Sine of pi over 2, what's the coordinate there? The y value is 1. That worked out because the two angles that I had to add added up to an angle that pi over 2 that I have already measurements for. If it added up to pi over 12, well, then that's no good. I'd have to go back and do it in pieces like this. But sometimes it works out that way, and then it's a little quicker. But if you don't notice it, then you go ahead and do it the other way. That's fine. Example 4. This example is a proof. So we've got the tan subtraction formula here, just like we've had sine and cos, but this one's tan. And this is what the right side of that formula looks like. Here's the left side, here's the right side. But I want to prove this, and I have to prove it using these two strategies. So this is kind of a weird question, but you do get ones like this. I'm proving a subtraction formula, but to prove the subtraction formula, I'm allowed to use the addition formula of the same function. So I'm going to prove tan of a minus b, and I'm going to use tan of a plus b to prove that. The first thing I want to do, I'm going to look at my left side actually. Usually when we do proofs, we start with the most complicated side, but this one's unique because it's a theorem that we're proving. So I'm going to start with my left side. My left side is tan of a minus b. Now, what I'm going to do is rewrite that as tan. So I'm allowed to use the addition formula here, right? So I want it to be a plus b in there, and then I can use that. So I'm going to write a plus, and then I'm just going to put my negative sign in with the b. Now I can use this formula right here because I have an a plus b. So my a will stay an a, that's still an a, but my b, when I substitute in for b, so instead of putting a pi over 3 there or a theta there, I'm going to put a negative b there, everywhere where I had a b. So substitute into this formula, a stays a, but b becomes negative b. All right, so that's all done. I used brackets to keep the negative b together. So this is a weird piece, this negative b. But here's our second clue, symmetry. Remember our tan has odd symmetry. That means that if we reflect it horizontally, it's the same as reflecting it vertically. That's going to help me get rid of this negative here. Instead of writing tan negative b, I can rewrite that piece right there. This piece right here, I can rewrite that as negative. So I'm going to make that a tan b now, but the negative is going to go in front. So I'm going to change that, and I'm going to change this. That's going to be tan a minus tan b now, because I moved the negative to the front because of the symmetry. I was allowed to do that. And then here we have 1 minus tan a, and I'm going to move that negative to the front. So I'm just going to put a bracket there. This is multiplied by negative tan, and now I have a positive b. So this negative, imagine this were a 3 here. I would multiply, bring the 3 out to the front. It's not a 3, it's a negative. So I'm going to, let me erase that, make it back to a negative. So my denominator now is going to be 1 plus tan a times tan b. Because I'm multiplying these two bottom pieces together, I can bring the negative out to the front. And then my numerator is tan a minus tan b. And what have we got? Well, we've got our proof. This is what we were supposed to prove. We proved the addition formula. We proved the subtraction formula using the addition formula. So my left side, therefore, my left side is now equal to my right side. So I've proven what I was asked to prove originally, because I've got both sides to equal each other. Again, I recommend you write down all of your theorems somewhere. You keep it on a separate piece of paper that you can pull out all the time, because you're going to have to keep adding more theorems to it as the unit goes on, and then it makes it a lot easier to do your homework when you can just quickly look it up and substitute in as you need to. The end.